In the CPP on C keynote, Herb Sutter showed some code with undefined behavior in C++. C++ can have UB when reading a local variable that is uninitialized. I decided to investigate further by looking into the assembly code. Herb did mention that this will get fixed in C++ 26, which is great news, but the point of this investigation is to learn what's happening in the compiler and see if we can turn on a compiler flag that's going to fix it and what that changes in the assembly. Let's get started by looking at the code that Herb had posted in his slide. We've got a function 1 here, a function 2, and we've got int main, which is calling function 1 then function 2. Function 1 is a character array of 7 characters, and in it we've got secret spelled out. In function 2, we've got another character array, which is of size 7, but this time we don't have it initialized. What do you think will happen if you print A? The behavior that you would expect is for A to be pretty much undefined, or set to 0, or something of that nature. However, in C++, turns out that if you print out A, you will print out the word secret. That's kind of the source of the problem, and why that happened was not clear to me, so what I decided to do was to essentially run this code through the debugger. So I created a makefile, and in the makefile I'm going to do 2 things. We're going to compile the code with Clang. Now this is going to generate the broken code. There's another part we're going to go through, which is the fixed version of this, which is by enabling the ftrivial auto var init equals 0 flag. This will automatically initialize this to be set to essentially zeros so that it won't print out the secret. One thing I want to do to make this easier for us is set some variables like this, just so that when we're going through the assembly, it's a little bit easier to read. What we expect is when we print this out to print out the variable hi, but because of the undefined behavior, it's going to print out HICRET, which again is the core of the issue. So let's run this and see what happens. Make, and I'm going to do v1 broken, which is just running the basic Clang command. So if I do /main, we're going to see the value of A is hi CRET. This is incorrect. Let's make the fixed version of this by doing make v2 fixed. This is going to run the ftrivial auto var init equals 0, and now let's see what happens when we run main. We see here that the value of A is high, which is correct. This is the undefined behavior that Herb was talking about in C++, and essentially what I want to do is go through the assembly line by line and see why this undefined behavior is actually happening. And of course, recall that I'm using the -g flag, which means we can run this through LLDB. Now, the first thing we're going to want to do is put a breakpoint on main. I believe it's target stop hook add disassemble, because that will show the assembly each time. I'm going to press done, and now I'm going to press run, and so here we're going to see that the debugger has paused right before calling the f1 function. In the assembly, it's performing a call operation, so let's step into that with si. I'm going to zoom out a little bit. Now, the next thing to look into is what is happening line by line in this assembly. We know that in F1, all we're really doing is setting up the A variable with secret in it. Let's go forward a little bit. I'm going to press SI. We've got a comment that's saying secret. So seems like we are trying to essentially inserting something into EAX, and the comment here is saying it's secret. So let's see what we're inserting into here. So I'm going to go one more line, and now we can do a register read $EAX. EAX has the hex value 72, 63, 65, 73. This is SECR in reverse. Let me show you how you can figure that out. So you could do print, you could do char to cast, and you could do OX72. That is R. So let's do the next two. So OX63, that is C65, that should be E73, which should be S. So as you can see, EAX essentially has SE C are stored in reverse. So essentially, we are filling out this register with the starting of the word secret. That's all this code's doing. So it's going through and adding some more. So AX is going to have ET, and finally the last one right here is going to be the null terminating character. And the other thing to note is that every time as we're doing this, we are updating RBP. EAX again had SERC in reverse, so we're putting essentially SERC at RBP minus 7. And here we're going to put ET at RBP minus 3, and then here we're going to put the terminating character. If we were to print 7 bytes of RBP, we should see secret. I'm going to press X for examine, /7 bytes like this, $RBP, and then we have to subtract 7, and let's see. So here we're going to get this value right here. I am not a hexadecimal magician, so I had no idea what this was, but turns out that you can convert this hexadecimal into characters by doing examine /7CB instead of 7XB, and there you go. You've got your secret word stored. All we're doing is storing secret. Right, we're just storing the secret, and this is totally fine. I just wanted to kind of walk you guys through a little bit of the assembly. In the next function is where the issue actually happens. So we can continue with an SI, and that's going to go all the way down here, and finally it's going to return. And now we are here, so I'm going to press SI once more to get to the next line. And once we're here, essentially what we're going to realize is that RSP, I believe, has the data for secret. We've moved whatever data was in RSP into RBP. So let's do examine with X /7CB/RSP. Oh, my mistake. We have to do minus 7X. There you go. This is kind of the issue, right? When we are essentially at this line of code right over here, we still have secret available to us, which we technically should not have. Right, so if I go to the next line, so now we are here initializing the first character in A. P, cast that into a character, OX68. There you go. So essentially this instruction right here is putting H into RBP at the 0th index, and this instruction, OX69, which is a very nice number, is putting I into RBP at index 1. We are overwriting values from the previous stack frame, but we should not be doing that. We should not have access to secret in the first place. So if I were to, let's go through these two steps. Let's do SI twice so we land right over here, right before we start our cout statement. So I'm going to do SI once, SI one more time. So right now we've completed these two actions, and if I were to inspect RBP, what we're going to learn is that it still contains the rest of secret. X7 examine the character bytes at RBP minus OX7, and this is the main issue here. You've still got CRET from secret. This uninitialized A variable still has access to secret from the, I believe, the stack of the previous function call, even though it shouldn't. So let's exit this. Let's go to creating the fixed version. Now, notice that the fixed version, what it's doing differently is creating the f trivial auto var init equals 0. This flag initializes simple variables to 0 so that you don't run into the issue that we did just now. It's using the same C++17 compiler, but I guess the point is that these compiler developers have started implementing C++26 features and putting them in flags, and essentially in C++26 this will be enabled by default. I wanted to kind of go through it and see what exactly is done differently by the compiler. How does it fix this issue? That's what we're going to do now. So we're going to make v2 fixed. So now let's do LLDB/main. Now we can run. We've not changed anything about the code. We've only changed the compiler flag. So let's see what happens this time. Again, we've stopped right over here at the call to function 1. which we can step into. Oh, the assembly is getting a little bit cut off, so I'm going to zoom out once more. Okay, cool. So this code has not changed. This is pretty much the same code as before. So cool, we've still got RBP with secret in here because that's essentially all this thing does right now. Now let's go to the next function and see how the assembly has changed after we've enabled the flag. Here we're going to see something different. There's a few extra instructions and I'm going to see if I can walk you guys through it. I believe we've still done the same thing up until this point. I believe it might be an RBP still, so let's see if it's an RBP. RBP. Ah yes, so it is still an RBP. So currently RBP still has secret, but this is where something interesting happens. What we're doing is these 3 extra assembly lines. This one is essentially calling memset. So memset, I believe, is a way to set the memory of a variable. And I believe what we're doing is essentially passing in zeros. XOR of a register with its own register is a 0. What we're saying here is 7. So for 7 bytes, set the memset to 0. So basically 0 out 7 characters. I don't want to step into this call function because that's going to take a while, but we're going to see that right after all these 3 instructions happen, that in RBP, we're actually going to have nothing in it. These are 3 instructions that are different with the compiler flag. So I'm going to do si, and I believe the next command that we want to do is not step into, but next instruction, because we don't want to go into it, we want to go to the next instruction. Cool. So here we've essentially done these 3 extra assembly operations, and this should clear out RBP. So we're doing the same thing again here. We're setting, 0x68 at the index 0 for RBP, and 0x69, nice, at the first index in A, but this time around, RBP should be empty. So let's confirm that, and let's do xcb $RBP minus 7 hexadecimal. So if you press enter, boom, there you go. Now the RBP has been set to 0. This is how the compiler is doing it. It's essentially adding these 3 assembly instructions, which is initializing the memory of the character array to be zeros, which if you recall in our makefile, that's exactly what we did. We essentially ran this compiler flag telling it to initialize it with 0. Anyway, this was very interesting for me because I personally had no idea that the following piece of code would have any issues. I don't believe it would have had any issues in JavaScript. Now, to be fair, JavaScript has a bunch of other issues, but anyway, it was interesting that this piece of code would leak this secret value in C++ 17 and maybe even C++ 20 if you didn't have that flag turned on. And that's because of how the value is stored in the, I guess, the register or the stack or whatever. And C++ has not yet cleared it out. Anyway, that was very interesting. I just want to explore that a little bit. Hopefully you guys learned a little something about, undefined behavior, C++, how you can solve undefined behavior and how you can solve it without actually having to do anything if you just wait and move this the standard to 26, and you should get this behavior fixed by default. Yeah, that's all there is for this video. I hope it wasn't too long. Thanks for watching, and I'll catch you guys next time.